I kind of got a little bored and decided I wanted to do a Putnam problem today. So the one I chose was A2 on the 2025 Putnam, so last year. Find the largest real number A and the smallest real number B such that ax times pi minus x less than or equal to sine x less than or equal to bx times pi minus x. So we're essentially using quadratic terms to bound this sine x term, or sine x function. And it has to be true for all x in the interval from 0 to pi. So I'm just going to start out by drawing this and making a sketch. So let's see, 0 to pi, so our interval is going to look something like this. Let's say like this is pi, this is -1, this is +1. So our function sine of x is going to look something like that. Okay, and I'll draw it in a different color even. So our function sine of x is going to be in red, and that's about as good as I can draw. And so we want a function that's going to be this quadratic, that's going to be an upper bound, and a similar quadratic that's the exact same except for the coefficient, that's going to be a lower bound. So the first question I asked is, if we're trying to bound this sine x by like quadratic somehow, let's try to see if sine x itself can be represented by a quadratic of some sort on this interval from 0 to pi. If sine x itself is like some sort of quadratic, then that makes the problem like really easy. And I'm guessing that's not going to happen, but I did it anyways. And so what I got was that if sine x is a quadratic, then we're going to have it's going to be some alpha times x times pi minus x. Since the zeros are going to have to be here and here, so that gives us this term. It's going to be some alpha times that is going to have to equal sine x. And so now we can just plug in values to try to figure it out. So the first value I plugged in was pi over 2, which gives us the value of 1. So if we plug in pi over 2, we get that alpha times pi over 2 times pi over 2 equals sine x. So alpha has to equal 4 over pi squared. So our function, or at least what we think, we don't know if this is true. So what we think our function sine x, might be represented by this quadratic, 4 over pi squared x pi minus x. So let me try to check that. So let's just choose, I don't know, like some pi over 4. And so pi over 4 is going to give us, we have the point pi over 4 radical 2 over 2. And so let's see if we can plug this in and see if that's going to happen. So we get 4 over pi squared times pi over 4 times 3 pi over 4, and you can see that it's probably not going to give us that. So if we cancel all terms, we get 3/4. And so 3/4 is not equal to radical 2 over 2. And so this function that we've tried constructing for sine x doesn't really work out because that function doesn't like hold for every point on the sine curve. So we can see that sine isn't like representable or like approximatable by a quadratic in like some sense of that word. So let's see, we have some function that's of the form x pi minus x, and so that function basically looks kind of like, well, I'll delete these, but that function is also going to share this like maximum point. So it could be like this, it could be under, or it could be over. And so that was kind of a question I had for those of you who like know these quadratics very well, or you could probably figure out that it's going to be over. But for me at the time, I didn't really figure that out. So what I did was, okay, I have this function. Is it going to be over the sine x curve or under the sine x curve? And so basically what I did was I just took the integral of this function from 0 to pi of 4 over pi squared x times pi minus x, and then I compared it to the integral 0 to pi of sine x. And you could have just like done the subtraction of the integral and see if it's positive or negative, but this also just works the same. It makes it a lot easier. So let's call this integral 1, call this integral 2. I'm going to do integral 2 first since it's easier. So this gives us negative cosine x from 0 to pi, which gives us a negative of -1 minus 1, so that equals 2. And so let's do the top one. So for number 1, I can take out the 4 over pi squared, and then we get x pi minus x dx. Oh, I forgot the dx is here. So dx equals, and we just integrate this. So this is going to be pi x minus x, so it's going to equal 4 over pi squared times, let's see, pi over 2x squared minus 1/3 x cubed. Yeah, so pi over 2x squared minus 1/3 x cubed from 0 to pi. And I also forgot to write the bounds. And so this equals 4 over pi squared times, let's see, so this gives us pi cubed over 2 minus pi cubed over 3. And the 0 gives us nothing, so we don't have to worry about subtracting again. And so this whole thing here is pi cubed over 6. And so that means our total thing is here is going to be pi over, or 2 pi over 3. Because 4, it's just this times this. So we have 2 pi over 3, and is it greater than or less than 2? And so pi is slightly greater than 3. And so since pi is greater than 3, 2 pi is going to be greater than 6. And so that's going to be greater than 6 over 3. So 2 pi is going to be greater than 3. And so basically using this logic, I found that our function here is actually greater than the sine function. And so what that looks like is, I think I'm going to need a better sine function to show this. So let me try to draw that. So like right at pi over 2. And then it's going to look like that, maybe. Let's get this one. And so what I found, if it's over, then we're going to have the quadratic approximation, and this is the smallest upper bound of the quadratic approximation. So this is the smallest real number b, such that this is still going to be greater than sine. And if we have any smaller number b, then it's going to either intersect the function, because the smaller number b is going to like make it like that. So this is the smallest number b, such that it's kind of like hugging the sine curve without crossing it. And it has the same like constraints. So that kind of gives us the upper bound. So we basically discovered this by accident, but that's actually the upper bound. So we can note that down. B equals 4 over pi squared. And so now we're focused on the lower bound. And so for the lower bound, let's go back to the graph. It's going to be like underneath here. And so I'm going to just try to draw a lower bound. It's going to be something like that. And it won't necessarily going to like touch this top part, because if it did, then like it won't necessarily touch the top part, because then this would itself would be like some quadratic approximation, this sine function. So it's going to be something like this. And the key like factor here that's limiting it, it's not necessarily the top part, like this peak here. The peak was the key limiting factor in the upper bound, but for the lower bound, the key sort of like limiting factor is this part right here. If we make it too big, then this side, it's instead of being inside, it's going to go outside of it. So this sort of like thing here, oh, I just deleted that, but this thing here is going to be a limiting factor, and this thing is actually the derivative of sine at that point. So we have that the derivative of our function has to be less than or equal to the derivative of sine at that point in order for it to be fully inside the function and still like have these two things. So that gives us an inequality. The derivative at 0, or I mean, you could do that pi and then you could do it the other way around because it's negative, but we would have that the derivative of the sine at 0, so we can have like d dx sine at 0 has to be greater than or equal to, or actually I'll just write this on the second page because we're running out of space. So we have I'll just d dx sine is just cosine. So we have cosine of x at 0 equals 1. So that's the derivative there. And that derivative has to be greater than or equal to the derivative of this function. And that function, derivative of that, that's just going to be a times pi, or a times x pi minus x. So we have that this function has to be greater than or equal to the derivative of this at x equals 0. So cosine 0, that's just 1. So 1 is less than or equal to the derivative of this function. So that's like, I mean, I guess I could have wrote like d dx right there. So just find the derivative. I can take the a out, and then we have the x here. So this is just pi x minus x squared. So the derivative is going to be pi minus 2x. So we have this function, we know x is going to be 0, so we can just like cancel this out. So it's going to be 1 is greater than or equal to a times pi. So a is less than or equal to 1 over pi. So that means our upper bound we have that the largest a can possibly be is 1 over pi. So let's go back up. Let's write a equals 1 over pi. So that's basically our lower bound, because if a were any bigger, then its derivative would be greater, and because of its derivative it's greater, it starts at this point, has a greater derivative, it's going to be on the outside now. And so that's how I intuitively like derive the answer to these. And so this is like the lower bound, this is the upper bound. And so that's how you intuitively derive the answer, but I don't really think that's going to be like a good solution to actually submit like a good proof. And so, I mean, a couple ideas I had for like actually formally like proving this is, first on this lower bound part, we would have to prove that, okay, yeah, the lower bound or this derivative is less than it, but we also have to prove that the derivative here like decreases at a faster rate than the derivative of the sine function. So this one is going to be completely underneath this one. So if this derivative decreases at a faster rate than this one, then we kind of have that this is going to be below this, and this is like the maximum we can get, because if we get an any bigger a, it's going to be outside. That's our argument there. And so we could basically prove that by taking the second derivative, because the rate of change of the derivative. So we just take the second derivative of sine is like negative sine, and then second derivative of this function is probably, I think it's just minus 2, and so I basically have to say that negative sine is always going to be like less than minus 2. And so yeah, obviously minus 2 is going to like has a higher rate of change of the derivative than the sine function here. So that's kind of like maybe a proof for the lower bound. And then about the upper bound, was one idea I had was maybe we could use like concavity or something, with saying that the sine function is actually like more concave than, or like more concave down than this like upper function here, because the upper function just like it opens up a little less. So like this would be like a super concave function, this would be like less concave. And if we show that the sine is like less concave than this one, and they have that like meeting point right there, then that would kind of mean that we can't squeeze anymore without intersecting it. Or we could just prove that like any smaller b would intersect with this sine function and therefore not be like fully above. I think either would work. So we could have to prove that any smaller b would intersect the sine function at 2 points instead of just 1. And that would probably like involve the like this quadratic term, or like whatever's on the square root of the quadratic term, the discriminant of the quadratic term, or something like that, I'm guessing. But that's kind of, I guess, my program for a solution, and this is how I derived it intuitively. So thanks for watching, guys, and I hope you liked it.